Hi, we're the Environmental Sensor Module Group. My name is Hilton, and we have my group mates Leo, Emily, and Jade. We would like to thank our sponsor, Dr. Keith Fenrich, for making all this possible. So, what are we? Just for some background, in biomedical research, typically when researchers are researching animals that are locked in vivariums, they cannot be around all the time to monitor the rodents, as they may leave to go grab a coffee or to chat with a colleague. So the solution to this allows them to monitor their subjects 24 hours or however long they desire, is to create an environmental sensor module. So it's basically a module that can capture the emitted vocalizations, the environmental data such as temperature, gas, relative humidity, and the visible light intensity. So you might be asking, why not just purchase a off-the-shelf module? So the pre-existing modules do not support microphones that record to 100 kilohertz at the moment, and they're not as customizable, and they're also pretty pricey. So our implementation would be able to cover all of those and keeping it at a reasonable price while leaving it pretty repairable. The project was expected to record vocalizations up to 100 kilohertz, measure the vibrations of the enclosure, and then measure the light intensity, temperature, humidity, and gas concentrations of various different gases. It also must have two recording modes, so continuous and triggered. So where continuous would record continuously and triggered would be where it would receive a 5-volt pulse, where in this case we simulated that with a button press to capture a recording from a window with a lag and lead time. So all the recordings obviously must be able to be retrieved from the device and put onto an external device such as the user's computer to analyze the data. Fortunately, all the requirements were met, and we'll be showcasing the device shortly.
This is a prototype of our environmental sensor module. The module consists of an accelerometer, an EnviroPlus board that consists of various sensors and an LCD, a ultrasonic mic, an external storage. Here we're using a USB flash drive, 2 buttons. One button is to start the continuous mode recording. The other button is to simulate a 5-volt trigger. This can later be replaced by connecting it to a device in the lab that sends out a 5-volt as the trigger. A Raspberry Pi 4. All the components are connected to the Raspberry Pi using a multiplexing board. Now allow me to demonstrate how our module works. Before powering on the module, make sure that everything is connected properly. The USB drive contains the configuration file for the parameters of the recording. The ESM program on the Raspberry Pi is set to start on boot. So now that everything is connected properly, I will power it on. You can see on the Raspberry Pi on the side, the lights are light up. So the Raspberry Pi is being powered on. It takes a while for it to boot up. So now we'll just wait for a bit. Once the module is powered on, we can see the module name display on the LCD. This means that the program is ready and we can start the recording. We will start with the continuous mode by pressing the white button. This is currently set to record for 1 minute. While the continuous mode is running, let's say a trigger happened, and we'll show this by pressing the green button. If you look on the LCD, you can see that both of the recording mode is on. Once the recording is complete and saved, the LCD will go back to displaying only the module name. So we'll just wait a bit until it's done. Now you see that the trigger is done recording, and what's left is the continuous recording. Now the recording is done. It is safe to power off, and we move the USB drive to retrieve the data. The USB onto a laptop, you can see that the recording files are stored here with both the triggered and the continuous mode in recording, as well as the environmental sensor data that are collected here and the accelerometer.
So what worked? So this project overall was actually quite successful, we'd say, although we ran into hiccups here and there, but in the end, our data came out pretty nice. So here we can see our data output. So that's the file, how they will be structured in the drive that you can remove. So everything's sorted nicely. So you can see the triggered environmental data, the WAV file, which is the voice recording, and then the acceleration data. So at the end, there will also be a general file for the accelerometer and the environmental. So that would contain the logs of all the data collected. Here we can see the microphone data pass through a spectrogram, so we can see that the mice vocalizations are clearly seen, so it would be roughly in the middle area. So it's a little bit hard to see, but 10,000 hertz is right around the middle, and the 100,000 hertz is the bolded number near the top. Here we have a sample file of the Enviro Plus data. So this was from the data output above. So everything's timestamped nicely with the temperature, pressure, humidity, ammonia concentration, and the light intensity. And here we have the accelerometer data. It's also the same as above, where everything is nicely laid out, showing like the movement in each axis. We were also able to stress test the device, and it held up pretty well. We stress tested for, I believe, 10 hours, and it was able to do like continuous recordings of that length. Realistically, the only limitation would be the storage you have. So I believe that the device under stress would work pretty well.
So what didn't work with our project? We had originally planned on the configuration file being hosted on a Google Drive. This would allow anyone using the ESM to easily make changes remotely while the device was deployed. The problem with this is that it required the Raspberry Pi to be connected to the internet. And the only Wi-Fi network available where the device was being deployed was the UWS network. This network required login credentials to access the internet. And upon restarting the ESM device, these credentials would be lost, preventing the device from receiving new configuration changes. Another problem we faced was that we couldn't validate our audio recordings. Although we were able to capture ultrasonic sounds, as seen in the spectrogram, we did not have the equipment required that could create a positive control tone at a specific ultrasonic frequency that we could then verify with using the spectrogram. Our last problem was with the continuous recording mode. When the ESM is used in the continuous mode for long periods of time, the recording will be segmented into 20-minute files. This is a result of the Pi's RAM size and the file format we chose. We use the .wav file format as it offers uncompressed capturing, and the Pi we used had 4 gigabytes of RAM. After 20 minutes, the RAM would be filled because of the large amounts of data created from capturing 384,000 samples per second. This limited our recordings to 20-minute chunks.
Now moving on to future avenues of improvement. One feature that could be pursued would be the creation of a graphical user interface, or GUI, for configuring the sensor modules. This would provide a more user-friendly means of configuring a module compared to editing its configuration text file. And if the user has multiple modules deployed, it would also allow them to configure all of their sensor modules from a single location. Another feature suggested by our client would be to implement more robust communication capability between the sensor module and its peripheral devices. The current design, as mentioned earlier, simply awaits a 5-volt pulse to start a triggered recording and is unable to receive additional information from the peripheral devices. Switching to a more robust communication method like a USB perhaps would allow metadata such as the specific device that generated the trigger, the animal that the device was interacting with, or the details of its activity to all be passed to the sensor module and included in the recording data. Another possible feature that was identified during our prototype testing would be to have automated timestamps when ultrasonic vocalizations are detected. As mice typically emit vocalizations for very short durations, typically in the range of 10 to 70 milliseconds, and they do so across a wide range of frequencies from 1 kHz to 100 kHz, it would be difficult and time-consuming for the user to manually comb through this data and try and identify these moments. It's therefore beneficial if the sensor module could automatically flag these moments for them. And lastly, there are a variety of quality of life improvements that were identified with the design. The addition of an enclosure would reduce the likelihood of damage during handling or the chance of short circuits when the module is mounted on a metal cage. The addition of a stop button to halt an ongoing continuous recording, and output the data collected so far would allow the user to prematurely end recordings if an experiment has ended early. And having some sort of indicator for when the module is still processing or initializing would let the user know when it's not yet ready to record. So, to conclude, the environmental sensor module is a cost-effective solution for monitoring environmental data and capturing ultrasonic emissions from lab animals, successfully meeting all of its functional and performance requirements laid out by our client, Dr. Keith Fenrich of the Faculty of Rehabilitation Medicine. We thank you so much for listening to our presentation.